Bienvenidos al 23º CIMAC. Gracias por estar acá. Vamos a comenzar hoy la sesión de modelación y sistemas dinámicos. Welcome everyone. Welcome to the 23rd CIMAC. We are going to start today the session of dynamical systems and modeling. And today we will begin with Professor Luciana Salgado. Luciana is a mathematician and a musician from Bahia, Brazil. Now she is living in Rio de Janeiro. And she got her PhD in math science at Federal University of Rio de Janeiro in 2012, where she has been a professor since 2018. She is a laureate with Women in Science from Bahia Prize in 2016. She also is the coordinator of the group Dynamic Women and the event celebrating women in math, both actions supported by women in STEM. So Luciana is going to talk about singular hyperbolicity and sectional Lyapunov exponent of various orders. Luciana?
Okay, thank you, Adriana. I would like to thank Adriana and the organizers for this opportunity to be here and to talk my research. It's a good time. Adriana is a good friend, and I'm very glad to be here. So, first of all, I would like to talk something about the history around singular hyperbolicity. This is a kind of weak hyperbolicity that emerged to be something like an extension of the uniform hyperbolicity theory. Okay, and this is because in the 1960s, by Ismail and Pallis, and believed that uniform hyperbolicity must work the most of the systems, but it's not true. And as we can see now, the Lorentz attractor is an emblematic example of robust systems that is not uniform hyperbolic. So to begin, so in this work, I introduced new notions of singular hyperbolicity and Lyapunov exponents, which we call sectional Lyapunov exponents of orders beyond the classical ones. The classical dimensions of expansion were two-dimensional and full dimension of the central subbundle. And after this, I obtained characterization of dominated split and partial and singular hyperbolicity in this broad sense by using Lyapunov exponents and quadratic Lyapunov functions. All right, our setting is this. We have any dimensional manifold with n greater or equal to 3, and we denote by this symbol the set of the space of set of C1 vector fields on M, and xt is representing its flow of this vector field here. And from now on, lambda is going to be a compact invariant set of the vector field. Okay. Its singularity in lambda is considered to be hyperbolic. It means that the eigenvalues of the vector field derivative have non-zero real part. Okay. And we say that a compact invariant set lambda is hyperbolic for a flow if we have a continuous invariant splitting in three subbundles, non-trivial subbundles one. This one is uniformly contracted, as you can see here. This is what this inequality says to us, that this bundle is uniformly contracting, and this one is uniformly expanding, like you can see here, and this one is the flow direction. Okay, the three subbundles are invariant and the non-trivial here we consider here. All right, and we say that a dominated splitting, lambda has a dominated splitting if we have that. Okay, here I'm defining it by two invariant subbundles. There are other definitions considering more, okay? But in my case, I studied the splitting in two subbundles, okay? So we say that lambda has a dominated splitting for x if we have the x invariant splitting in two subbundles, E O plus F, which are non-trivial, okay? And for every x in lambda, for every point in lambda, there are these positive constants, such that we have this kind of correlation, decay of correlation. This means that if we have no contraction here, we have expansion here, and if you have no expansion here, we have contraction here, but we don't know where it is uniform, the contraction and the expansion, okay? So this is a kind of feature that has been studied for many and many renowned researchers in mathematics, in particular in dynamical systems, and it has been considered the weaker form of a hyperbolist until now, right? So this is another kind of a weak hyperbolist. We say that we have partial hyperbolicity on lambda for x if you have a dominated splitting E plus F, such that E is uniformly contracted or F is uniformly expanded by the cocycle of the flow derivative. This is, again, this is a weaker form of a hyperbolicity that is very studied now, and you can see, as you are interested in dynamical systems, that this is an important part now of our research line. All right. By now, I'm going to define a singular hyperbolist, a sectional hyperbolist. The definitions, what I'm doing here, are for flows, for vector fields, but it can be done to diffeomorphisms too, okay? And the singular hyperbolist, no. It is only for flows or vector fields which admits singularities or equilibrium points accumulated by regular ones, okay? And this is because it's called the first definition by Morales, Pacifico, and Pujals was called to be singular hyperbolicity, because it has to do with the singularities inside the the regular set, okay, accumulated by the regular set. So to do my definition, I'm going to consider vector space E and denote by wedge PE, the PETH exterior power, which is defined as follows. We take a basis of the vector space E, suppose V1, V2, and Vn, and we generate the exterior power of E by this exterior product, where the index here vary between 1 and n, okay? We take P products, P exterior products, and we vary the index between 1 and n, okay? Okay. And once we have this, any linear transformation uses another transformation which called exterior power of A. And moreover, we can view as any P plane as a P product, P exterior product, okay, generated by those vectors here, and we can take these vectors, if we call this exterior power by V tilde, sorry, by V tilde, then we can see this vector field of norm 1 to represent this P plane, okay? So to get singular expansion or sectional P sectional expansion, we just need to have some constant lambda greater than 0, and for every t, for every time t, positive t, we got the following inequality: the exterior power of the flow derivative applied to the tilde is greater than c exponential lambda t. Okay, this is the math word to the singular expansion. And now we say that lambda is singular hyperbolic. This is the first definition in the history of the singular hyperbolicity. If we have the composition of the partial hyperbolic splitting of the tangent bundle in two subbundles, where this one is, as it is partial hyperbolic, this is contracting, uniformly contracting, and the subbundle F is volume expanding. This is the determinant of dxt over F, okay? Because D is the dimension of F here. So the two-sectional hyperbolicity is when we have this splitting, partial hyperbolic splitting, and the flow derivative expands planes, two planes, b-dimensional planes in F. Okay, this is a particular case of this one, right? If you have expansion of any two plane in F, of course you have the volume expansion here, right? This is a kind of characteristic of the two-sectional hyperbolic flows and singular hyperbolic ones. And then I have made the following definition. We say that lambda is sectional hyperbolic of order P if there exists a partial hyperbolic splitting E plus F, such that E is uniformly contracting, and the central subbundle is, we call it central, and the central subbundle is P-sectionally expanding, and I consider here P any number, fixed number, between 2 and the full dimension of F. We can also define it for P equal to 1, but it's not so common in the literature here. Okay. Well, from now on, we are going to use the term sectional hyperbolic without mentioning the dimension, okay, except if it is necessary. So this is our first example of a two-sectional hyperbolic system, the geometrical Lorentz attractor. It was constructed by Buchenheimer and Williams to have an example of behavior as the Lorentz equations. We know that Lorentz have made numerical experiments and got some kind of strange attractor. This attractor was not hyperbolic one or uniformly hyperbolic one, and Buchenheimer and Williams constructed this example to simulate the behavior of the Lorentz equations geometrically. So this is an example of two-sectional hyperbolic system. Here we have a singularity, which has one expanding direction and two contracted direction. Okay, and the feature here is that this eigenvalue wins the weaker one. Okay. So the sum of both is greater than 0. This is because it has a two-sectional expansion. So why define sectional expansion of dimensions between 2 and the full dimension? Okay, because we have example of this. Trev and Shilkov constructed an example of a singular attractor such that in any dimension we have 3 sectional expansion in one subbundle, and we have no 2 sectional expansion. So this is the motivation to study the dimensions between 2 and the full dimension of the sectional hyperbolist. Okay. All right. So what can we do with this? This is like a new definition and notions, and we want to make research with this, right? All right. And first of all, we can think about the dominating split, the domination property, because all of the notions of weak hyperbolicity here, it's used the domination property. So the question is, to make some characterization of weak hyperbolicity, first we have to make some kind of characterization of domination property in this kind of notions that I have here. All right, okay. But in my thesis, I have made a condition, or discovered the condition to base it on the two sectional hyperbolicity. Okay, if you have a compact invariant set for a vector field, one vector field with all singularity hyperbolic, like hyperbolic here, saddle type in the most of cases, and suppose that we have a continuous invariant splitting of the tangent bundle on lambda in E plus F, where E is uniformly contracted and F is sectional expanded. The question is this a sectional hyperbolic splitting? Look, I have uniformly contraction and sectional expansion, but I'm not supposing here that it is dominated. Okay, this is to see that we want to get dominated split. But in this hypothesis, we have to consider the decomposition over the singularities, because the singularities here can be accumulated by regular arcs. And then if the decomposition in the singularities don't match with the decomposition over the regular points, it's not a dominated splitting, because the dominated splitting have to be defined over the whole set, okay? And to be continuous, it have to be compatible with the splitting over the singularities. So, okay, we have contraction, we have expansion, sectional expansion, and we have to consider dominated splitting matching with this splitting here. And then, yes, we got a dominated splitting for E plus F. Okay? All right, good. It was a good goal, but we can ask how to take off the condition of our singularities, because this is a restrictive condition. Okay. All right. Let me see. I got something. A characterization of domination property based on exterior powers with Vitor Araújo. We got the following. Suppose that we have an invariant splitting E plus F on lambda, okay? And the dimension of F is equal to K greater or equal to 2. Consider F tilde, the kth exterior power of F, and the xt invariant, the k exterior power of the xt, the flow derivative invariant subspace generated by the vectors of F, and the tilde is complement over the exterior power, okay? Such that E tilde plus F tilde is a splitting of the exterior power over Tm, T lambda m, and then the first, the splitting for the flow is dominated if and only if the splitting of the kth exterior power is a dominated one for the exterior power 2. But look, K is equal to dimension of F. Okay, this is another restrictive feature, because if we take k less than dimension of f, it's no longer is true. Okay, I'm going to show you an example of this now. Suppose we have a hyperbolic singularity, okay, in a 4 manifold. We are here in dimension 4, such that the derivative of the vector field over sigma is the diagonal of -2, 1, 3, and 10. Okay, this is a very simple example, very simple. And consider the following splitting. We consider E like R, the real line, times the origin in R3, and consider F, the origin in this line, times R3. Okay? This is a dominated splitting, okay? Because we have -2 here, and all singularities here wins like this over the sum of this one wins the eigenvalue here. Okay, but if we take k equal to 2, which is less than 3, which is the dimension of f, then the splitting at tilde plus f tilde of the exterior square is not dominated. Indeed, we have the following eigenvalues for f tilde. We have 4, 11, and 13. And for a tilde, we have -1, 1, and 8. Okay? So when we look at the eigenvalue 8 and compare it with the eigenvalue 4, it is strictly bigger, and then it wins in expansion. So it cannot be a two dominated splitting. There is no two dominated splitting between a tilde and f tilde. Okay, this is our example why in the previous theorem we need the restriction of the dimension. Okay, but it's right, it's characterization, but I would like to have a characterization of dominated splitting without use exterior powers, you know. So I got the following. First, I'm going to define a total probability set. We say that gamma inside lambda is a total probability set in lambda if for every x invariant probability measure mu, hold that mu of gamma is equal to 1. Okay. So what I got, suppose that there is a continuous invariant splitting of the tangent bundle on lambda, E plus F, and then this is a dominated splitting if and only if there exists eta less than 0, a number eta less than 0, such that this kind of correlation here happens. This is a gap, this is a spectrum-based characterization of the dominated splitting. This is a full characterization of dominated splitting, which does not depend on singularities, exterior powers, or even anything that we had before. Okay, this is an ergodic characterization of dominated splitting, right? And this is very useful for investigation in weak and uniform hyperbolist All right, but my question is how to take off the continuity condition here. Okay, I'm working in it. I have some ideas, but it is still open question to think about. Okay, so let's go. From now, I'm going to define the Lyapunov functions that I have mentioned in the introduction. Some question? No? Be free to question me, okay? And I'm going to define the tools to make the proof of this theorem here. This is the only one that I'm going to make a sketch of the proof, okay? But this is a kind of tool that is very useful in many works, Markarian, Katok, many people used Chernov, let me see, many people used quadratic forms to make works on dynamical systems, and I'm going to use the approach of Wojtkowski, who made use of the theory of J-algebras of Potapov. Potapov was a Russian mathematician who have made this approach of quadratic forms. Okay. Well, and we consider here J as an indefinite non-degenerate quadratic form on the tangent bundle over M. We denote C plus or minus X, the open cones, like this, defined like this, positive and negative cones of vectors, and C0 is their common boundary here, where J is 0. And given a field of non-degenerate quadratic form J, we say that ecocycle ATX over the vector field capital X here is J separated if AT takes the positive cone over X inside the positive cone over XTX, okay, for all t greater than 0, and we have here a neighborhood where the flow is defined. U here is this neighborhood where X is defined. And we say that it is strictly separated if it takes the positive cone with its boundary strictly inside the positive cone over the flow. This is J monotone if the function J is a monotone function, and strictly monotone if J is strictly monotone function, which means this, and isometry if J is an isometry on Tm. Okay. All right. This is our main definition now. Okay. So let's go. this is the geometric view of the strictly separation. We take the positive cone, and this is taken to inside the positive cone there when we flow it by the vector field. Okay. This is not a new feature. We know that we can define hyperbolicity, for example, by using cones, but those cones are generated by a quadratic form. This is the good feature here. Okay. So when we have a separated linear operator L from a vector space here V, then we can look to the linear algebra over this operator. Okay, and we have a polar decomposition of the operator by the quadratic form, the indefinite quadratic form J. We can uniquely represent L by R times U, where U is an isometry and R is symmetry, or we can also say pseudo adjoint with positive spectrum. Okay, this is really a good feature here. It is to make easy our computations. This operator R can be diagonalized by a J isometry. Okay, and the eigenvalues can be ordered in this way, in 0 less than RK less or equal to, etc., R minus 1, which we call R minus here, which is less or equal to R plus, and then we go to complete the dimension of the space. Okay, and when we have this kind of order of the eigenvalues, we have this characterization here. L is monotone or strictly one if and only if we have that R minus is less or equal to 1 and R plus is greater or equal to 1, and strictly if this inequality, those inequality here are strictly 1. This is very good to look at to the hyperbolicity of any separated operator. All right. My theorem is this. We consider a compact invariant set lambda whose singularities are hyperbolic, and the index of the singularities are greater or equal to the index of J. Index here is the dimension of the contracting space of lambda, and the index of J is the dimension of the R minus eigenvalues. Okay, and then we say that we can prove that lambda is p-sectional hyperbolic if and only if there exists a neighborhood U of lambda and a field of non-degenerate quadratic form J, okay, on U with index varying between 1 and n minus 2, such that X is non-negative, strictly J separated, and the spectrum of the diagonalized operator dxt satisfies the following properties. r minus 1 is less than 1, and the product of the, I'm going to say positive, but it's not, because r minus is positive too, okay? The positive index, r positive index, the product of the r positive is greater than 1, where p here is greater than 2, greater or equal to 2, and less or equal to the dimension of m minus the index of j in a total probability set. This is a full characterization of sectional hyperbolicity by using Lyapunov quadratic functions. Okay, and this is very good because we are using pseudo-linear algebra here, so we can make accounts easily, I think. All right. Okay. To go on, I'm going to define the linear Poincare flow Pt of xt along the orbit of the point x by projecting the image of the vectors under the xt action orthogonally over the pseudo-orthogonal complement of the flow direction here with respect to j. This is the mathematical face of this projection, okay, and Pt is here, linear Poincare flow, LPF, is the projection over the XTV, okay? This is we say that the linear Poincare flow is monotonous if we have the characteristic of monotonist by J over Pt, okay? This is the geometric figure of the linear Poincare flow. We have here the normal subbundle with respect to the flow direction, the vector field direction. We have a tangent vector field vector here, V, right? We project it orthogonally over NX. We flow it by the vector field. This is the image of V over the derivative of the flow and we project again. Okay, then it gives a real flow for us, which we call linear Poincare flow. Okay. All right. So let us see what motivated to study it in my thesis. We have considered a diffeomorphism over a closed manifold and B, a quadratic form on the tangent bundle of M. Consider the quadratic form called the push forward of B is like this. We apply the quadratic form in the point fx to the derivative over x to v, okay? This is f sharp bxv. And in the 1980s, Leibovitz has proved that a diffeomorphism, a CR diffeomorphism, is anosoph, or which means it is hyperbolic over the whole manifold, if and only if there exists a continuous non-degenerated quadratic form B, such that this quadratic form here, the push forward minus B, is positive defined quadratic form. So this is a characterization of hyperbolic feature of a diffeomorphism, and Wojtkowski, based on this and using quadratic form, the algebra of Potapov, has proved that if the linear concave flow of a smooth flow is strictly J-monotone, then the flow is a Nosov, which means that the whole manifold is hyperbolic. Okay, this is a motivation to sorry, I have 5 minutes left. It is?
Yes, Luciana.
It was not 1 hour.
It was
okay.
15 minutes.
I thought that it was an hour presentation. Okay, okay.
Okay.
I'm going to go to the final. I'm not going to prove with Ben this property, but I'm going to define the bisectional Lyapunov exponent here. Is like a Lyapunov exponent, but we use the exterior power, and I have that a set is partial hyperbolic if and only if the Lyapunov exponents on E are negative or positive on F. We have dominated splitting. This is the application of my main result here in a total probability set. This is a characterization of partial hyperbolicity. And I got again, by using Lyapunov exponents, sectional Lyapunov exponents, and the main result here, a characterization of p-sectional hyperbolicity, if lambda is p-sectional hyperbolic, if and only if in a total probability set, we have this kind of gap of the spectrum, Lyapunov exponents in the E direction negative, and positive p-sectional Lyapunov exponents on F. This is a full characterization of p-sectional hyperbolicity by using this feature based on Lyapunov exponents. And this is a characterization of partial hyperbolicity by using quadratic forms. Is the generalization of the theorem of Lebowitz for partial hyperbolic flows. Okay, and okay, I'm going to go on. I'm not define star systems because it is application of the quadratic forms here. An example of star systems is the Lorentz attractor. This is a simulation of my female student Manuela Monteiro. We got this by Octave, and I have the following characterization of star systems. We define the quadratic forms of the per-period points. The singularities are strictly J-monotone, and the linear Poincare flow is J-monotone too. To finish, what about the ergodic properties? Okay, Pacifico Yang got us entropy expansive two-sectional hyperbolic set. And in my future works, I intend to study the ergodic properties of sectional hyperbolic systems in broad sense. And if you are interested in this research, please let me know. And thanks, gracias, danke, merci.
Thank you, Professora Salgado. Are there any questions?
Hi.
Hi.
Hello, Luciana, tudo bem?
Tudo bem.
Congratulations. It was a very nice talk.
Thank you.
So I have
Yeah.
a small question. Can you go back to your main theorem, please?
Yes.
Uh,
Flow. Let's flow.
I think that,
yeah.
this
Here.
one. So here you have a dominated splitting in a total probability set, right? Under the condition of this gap.
The domination is over the
Of the whole space.
yes, the whole space.
Okay.
But this feature here is needed to be in total probability set. The gap.
The gap. Okay, in total probability set. This is just the gap between the Lyapunov exponent, right?
Yes. Yes.
And is it possible to translate this result in terms of linear cocycle, for instance, fiber bunch cocycles?
I think so, because if you see at my first my second paper with Vitor Araújo, my first paper with him, but my second paper is infinitesimal Lyapunov functions and blah blah blah. The account that I have made with the quadratic form that I used here to prove this, it's made two cocycles over the vector field, and I think that is a good idea.
Because I'm asking because there is a recent paper by Kassel and Potri. They prove that this is for locally constant cocycle. If you have this gap, uniform gap, you have a dominated splitting of the whole space. And the question they left is that, is it true for fiber bunched cocycle? And the idea of the proof use a characterization of Boki. It didn't use the Cornfield criterion. So they use another approach. The characterization, use singular values, decompositions.
Yes.
That's why I'm asking. Thank you so much.
Yes, we can see it.
Okay, it would be nice. I'm working with Adriana to try to extend that result for fiber bunch
Very
cycle.
good. I think that those tools here is a good idea to use to prove this. Yeah.
Okay. Thank you.
Thank you, Yaya. Are there any other questions? If not, let's thank Professora Salgado again. Thank you very much for your presentation.
Thank you.
Good to see you.
Yeah, that's the only way that we can get together, right? During these events.
At least.
Yeah.
Well, we have a little time. I don't know.